In this video, we are going to go over section 10.1 and 10.2. The goal of section 10.1 Taylor polynomial is to review higher order derivatives and use the Taylor polynomial to estimate the value of computation. So for example, if we had a function value, let's say cube root of 2, one way we can get that value is just directly use the calculator, enter cube root of 2, and you get a value. But instead of using the calculator, we are going to come up with a polynomial called a Taylor polynomial and use that to approximate cube root of 2. So that's the goal of the section. So let's start with the definition and then work on some example problems. Definition, Taylor polynomial at 0. If f has an n derivative at 0, then the nth degree Taylor polynomial for f at 0 is defined as p sub n of x, a sub 0 plus a sub 1 x plus a sub 2 x squared plus l all the way to a sub n x to the n. So each a are my coefficient, and then x squared all the way up to whatever the nth degree, that's gonna be the term. Where p sub n k sub 0 is f of k sub 0. So f of k sub 0, this term is used as an nth derivative of function. So if you have f sub 2 sub 0, that means second derivative. So let me do a little bit of elaboration. So f of 2 sub 0, this does not mean an exponent. This means second derivative at 0. So you can think of that k value as any of the number of degree that you need to differentiate. So more concise form is following here, p sub n, and then they define it. And then each a sub n or a sub k is your derivative function. You differentiate second time, substitute 0 divided by 2 factorial k. Sometimes the polynomial can be centered at certain value, then you have a. You don't always have to differentiate at 0, maybe 2 or 3. Then your Taylor polynomial series is defined as this below. Okay? So keep that in mind, and we'll use the definition to come up with the polynomial. So the first two questions is just practicing and then getting used to taking the derivative. So we have a function f of x equal ln of 5 plus 7x, and it's just taking third derivative. So we'll differentiate 3 times. So first derivative, f sub f prime of x. So the derivative of ln x is a 1 over x, but it's like there's a u involved, right? The 5 plus 7x. So the first derivative will be 1 over 5 plus 7x, and derivative of 5 plus 7x is just 7. You can put that simplifying 7 over 5 plus 7x, or you can even use a exponential form. 7 times 5 plus 7x, raise it to the negative 1. I personally prefer writing it as an exponential form rather than a quotient, because quotient rule, if you recall, it's a messy one, right? So I like having this power function. So let's take a second derivative. I'm going to use this power function. So bring down the negative 1 in front. So that's going to make negative 7. 5 plus 7x. Subtract by 1. So I'm having negative 2. And then derivative of our chain, which is 5 plus 7x, which is 7. Simplifying, I'm going to get negative 49 times 5 plus 7x, raise it to the second power. Let's take third derivative. They ask you to do third derivative. So same thing, Negative 2 comes down, multiplies with negative 49, so it is 98, positive 98. 5 plus 7x, raise it to negative 3, and then derivative of 5 plus 7x, that's just 7. Multiplying 7 and 98, I'm having 686 times 5 plus 7x, raise it to the negative third power. So that's my third derivative right here. Number 2, fourth derivative, so we do it 4 times. This is an exponential function. So basic formula for the exponential function for the e to the x is e to the x dx. So recall that. So the first derivative, e to the negative 2x, that's a e to the negative 2x, and then derivative of the exponent is negative 2. So negative 2 times e to the negative 2x. Second derivative, so second derivative is negative 2, e to the negative 2x, and then our exponent, negative 2 again, so it's going to make 4 e to the negative 2x. Okay. Third derivative, so third derivative is this coefficient, and then this whole thing remains the same, and then we just have to take the derivative of our exponent. So there's my 4 e to the negative 2x, and derivative of negative 2x is negative 2, making negative 8 e raised to the negative 2x. Okay. All right, my fourth derivative, you can, at this point, you can use this apostrophe, and if it gets too much, you can start writing this notation, f to the fourth x. That's not an exponent, that is a differentiable notation. So this f of k sub 0, that's your differentiable notation. Okay. All right, so my fourth derivative, again, this part remains the same, and we just have to multiply by dx of this one. So we have negative 8 e to the negative 2x times negative 2, which makes it positive 16 e to the negative 2x. So 1 and 2 is just a review. Okay, we have done taking the derivative back in Math 121. Okay, so it's just reviewing, and then just keep taking higher order derivative. Now, number 3 is our main problem. We need to find the third degree Taylor polynomial of our function f of x cube root of x plus 8 and use that to approximate cube root of 10. Okay, so again, the purpose of Taylor polynomial, what we are going to do is we are going to come up with the Taylor polynomial to estimate the value. So whatever the function is, we are going to use it to approximate cube root of 10. And I'm going to use a calculator to compare and see how accurate the number is. So let's come up with the Taylor polynomial in its third degree. So that means we have to take derivative at least 3 times, because n is your 3's. And this is the one that I'm going to be using, this one right over here. Okay. Because it's asking you to write it out at 0. Okay. So we need to take the f of 0, take the first derivative, plug it in 0, and then second derivative, plug it in 0, all the way up to the third. So I will differentiate first, and then substitute the 0 to get my coefficient term, and then divide it by the factorial part, and then add our variables. Okay. So step 1, let's find all the derivative. So your first derivative is, your original function is cube root of x plus 8. However, I'm gonna write it as x plus 8 raised to the 1/3. which is more friendly way of writing it for the differentiating. So I'm using power rule. Bring down the 1/3 down, subtract by 1, and multiply by the derivative of x plus 8 chain rule. So first derivative is 1/3, and then x plus 8. 1/3 take away 1, so it will be negative 2/3. Same thing, taking twice. We need to go 3 times because they want third degree. So negative 2/3 comes down, multiplies with 1/3, making negative 2/9. X plus 8. Negative 2/3 subtract 1 is negative 5/3. Third derivative is negative 2. Third derivative will be positive because negative times negative. And if I multiply these two, I'm going to have positive 10/27. X plus 8. Subtract by 1, negative 8/3. Okay. Step 2. Once we have all these, we need to substitute value with zeros. All those differentiables function at 0. So let's do that. So step 2, f of 0. So I'm going to take this one, plug it in 0 for each one. And that's going to be my coefficient value. So f of 0, 0 plus 8, 1/3, that's 2. F prime of 0, so that's 1/3. 0 plus 8, negative 2/3. You do that, pull out the calculator, and then, so 1/3, this is 8, raise it to the negative 2/3, that's 1/4. So I get 1/12. Second derivative, negative 2/9. 0 plus 8, negative 5/3. So I'm having negative 2/9. And then 8 raised it to the negative 5/3 is equal to 1/32. So that's negative 1/288. Lastly, f of 0 at the third derivative function. So 10/27. 0 plus 8, negative 8/3. So that's gonna be 10/27. 8 raised to negative 8/3 is 1/256. So I'm having 1/, and you can cancel this out, the 10, and then 256, and then make it 6912. Okay. All right, now step 3. So step 3, what do I need to find? These, right? So we got this, we got this. I have the second derivative, but I have to divide it by 2 there. And my third one will be divided by 3 factorial. So I'm going to find the coefficient of the Taylor polynomial by putting 2 factorial and then 3 factorial. So step 3, find the coefficient of the Taylor polynomial. So a sub 0 is just f of 0, 0 factorial. So that's going to be f of 0 is 2. 2/0 factorial is just 1. So it's 2. A sub 1 is f of 1, 1 factorial. So that's, I'm sorry. That's f prime of 0. So f prime of 0, we got 1/12 right over here. So 1/12. over 1, which is 1 over 12. Okay, a sub 3, a sub 2, I'll put it over here because I'm running out of space. A sub 2 will be f double prime of 2 of 0, and then 2 factorial, so that is negative 1 over 288 divided by 2 times 1, which is 2. So I will be multiplying 1/2, multiplying 1/2 gives me negative 1 over 576. A sub 3, f triple prime of 0, 3 factorial, so that's going to be 1 over 6912, 3 times 2 times 1, which is 6. So I'm going to be multiplying 1 over 6, 1 over 6 to get rid of it. I have my final answer will be oops. I think I made a mistake. Hold on. Give me 1 second. Two, 1 over 12. Negative 1. Okay, and then let's see. 3 times 2 times 1, so 6. And then f triple prime 1 over 6912. Yep. Oops. Yeah. Actually, never mind. So I have 1 over 6912, 1 over 6912. For some reason, I thought I made a mistake by copying that, but I have it all. So if I multiply that out, my final answer is going to be, let's use a calculator. 256. I'm going to have 5 over 20736 times 6. Okay. All right. 288 times 2, 576. So what is my Taylor polynomial look like? I'm going to add a page. Let's add a page, blank page, and then add it over okay. So my Taylor polynomial, so finally the Taylor polynomial at p sub 3x is going to be, here's my coefficient, two 112 negative 1 over 576, and then 5 times 5 over 20,736. So my piece of 3 will be 2 plus 1 over 12x. So don't forget, you need x here, and then x squared, and then x cubed, all the way up to x cubed term. Minus 1 over 576 x squared plus 5 over 20,736 x cubed. Okay, so now let's compare. Find the appropriate value of x so that we can use to approximate cube root of 10. That's what we wanted to do. We want to use our Taylor polynomial to approximate cube root of 10, and then we have to find out what the x value will be. So we have the polynomial, original polynomial is cube root of x plus 8. If I want that to be 10 underneath, I can solve for x by cubing each side. X plus 8 equals 10. Subtract 8, x has to be 2. So I'm going to be using this one, plug it in to our polynomial that we created over here. Okay, so if you do that, we have 2 plus 1 over 2, substitute 2, negative 1 over 576, 2 square, plus 5 over 20,736, 2 cube. Okay, this one disappear, right? Oh, not disappear, that's a 12. I made a mistake, 12. So 2 goes into 12 6 times, so that's 2 plus 1 over 16. That's a 4 here, 2 square. And then simplify, you're going to have negative 144. This is 8, 2 cube, 8. Cancel with 20,736 by 2,592. So plus 5 over 2,592. If you put everything onto the calculator, so 2 plus 1 over 6, subtract 1 over 144, plus 5 over 2,592, I get in a decimal value 2.1617. Now, how accurate is our answer? If we actually pull out the calculator and then check what the cube root of 10 is, right? Cube root of 10 is, let me, 2.1544. So this is approximate. This is 2.1544. So we were pretty accurate. Okay, we have 2.1617, and then the actual value is 2.1544. Okay, so this is a one way of using Taylor polynomial to approximate a function value. Okay. All right, so let's do one more together. I believe this is the last example, and that's number 4. Another practice of coming up with Taylor polynomial, and this is again a third degree, and we are gonna use it to approximate cube root of 2. Okay, so same thing. Step 1. I'm going to need to differentiate 3 times because I want third degree. So f of x, again, writing in an exponential form, 1/3. First derivative, 1/3 comes down, raise it to the negative 2/3. Double derivative, second derivative, negative 2/3 comes down, multiplies with negative 1 and positive 1/3, making negative 2 over 9. X raise it to the negative 5 over 3. And then triple prime or third derivative will be, again, negative 5 over 3 comes down, multiplies with negative 2 over 9, makes it positive 10 over 27. X raise it to the negative 8 over negative 8 over 3. Step 2, they want you to differentiate not at 0, but this time a equal 1. So I'm going to be substituting f of 1 this time instead of 0 because they give you value as 1. So 1 raise it to the 1/3, that's just 1. F prime of 1, that's 1/3 times 1 raise it to the negative 2/3, which is 1/3. F double prime of 1, negative 2 over 9. 1 raise it to the negative 5 over cube. Now anything cube root of 1, that's 1, so it's negative 2 over 9. F triple prime at 1 is 10 over 27. 1 raise it to the negative 8/3, which is 10 over 27. Okay. Now let's find the coefficient of Taylor polynomial by putting the factorial term underneath. So each a sub 0, a sub 1, a sub 2, a sub 3. So step 3, find the coefficient of the Taylor polynomial. Okay. A sub 0, this is f of 1 over 1 factorial. So that's f of 1, which is just 1. A sub 1, that's f prime of 1 over 1 oops, that's a 0 factorial because my n is a 0. So over 1 factorial, so that's just f prime of 1, which is 1/3. A sub 2 will be f double prime of 1 divided by 2 factorial, which is f of double prime of 1 divided by 2, because 2 times 1 is 2. So we get negative 2 over 9 divided by 2, reduced down to negative 1 over 9. A sub 3 will be triple prime of 1 divided by 3 factorial. So that's 10 over 27. 10 over 27 right over here. 3 factorial is 3 times 2 times 1, which is 6. So 1, 6, 1, 6. Cancel this 3 times. This one 5 times. So 5 over 81. So my Taylor polynomial at p sub 3 will be each a's term, the coefficient, so 1, 1/3, negative 1 over 9, and then 5 over 81. But this time you have it at 1 instead of 0. So a is 1, so we would subtract x minus 1 all the way up to x minus 1 cube. So we have 1 plus 1/3 x minus 1 minus 1 over 9 x minus 1 square plus 5 over 81 x minus 1 cube. Right. Find the approximate value. So the last part is we want to use this p sub 3 polynomial, the Taylor polynomial, to approximate cube root of 2. So your x this time, you can see that it's just 2. So we are going to be substituting p sub 3 of 2. So 1 plus, this is the one part, that's first answer. Now I'm going to approximate 1/3, 2 minus 1, negative 1 over 9, 2 minus 1 square, 5 over 81, 2 minus 1 cube. So let's keep going, simplify. The first term is just 1. This is 1 times 1/3 plus 1/3. That's 1. That's a negative 1 over 9. And then plus, this is 1 again, so 5 over 81. And then if you put that on the calculator, I get about 1.2839. So this is approximation for cube root of 2. Now, this is kind of like checking what is actual value of cube root of 2. How accurate is it? So we can also check. So if you actually do cube root of 2, it is 1.2599. It is 1.2599. So again, we were close, right? 1.2839, 1.2599. Okay. All right, so that's the end of section 10.1. All right, now we are gonna move on to 10.2, which is the Taylor series. Okay. So Taylor series, the goal of this section is to determine the interval of convergence for the Taylor series. So recall back in Math 121 when we had a limit, right? And then some limits were converged and some limit function diverges. So certain polynomial converges in certain interval, and then some diverges once you pass that interval. So we are going to use Taylor series to see at which part converges. Okay, so here's the definition of a Taylor series. If a function f with the derivative of all orders at a point A, P sub n sub x is the nth degree Taylor polynomial for f at A, and A sub n is f of n A divided by n factorial. And this is something that we have already seen it. That was earlier one, this formula, the coefficient. Okay, so it follows very similar. Okay, so the Taylor series converge at x if the limit at the Taylor polynomial as x goes to infinity equals to the sum of our Taylor series here. Okay. Exists and diverges of x if this limit does not exist. Okay, so if limit does not exist, we say it diverges. Theorem 1, interval of convergence. Let f be the function with the derivative of all order at a point A. Let A sub n be the coefficient of our Taylor polynomial. Then there are 3 cases, and this might look very familiar. That's actually a ratio test. Recall from 121, a ratio test. So we have we are going to take the derivative, we are going to take the limit as n approaches to 0 of our Taylor polynomial coefficient a sub n plus 1 divided by a sub n. If it's equal to some number L where that's greater than 0, then R is 1 over L, and then we call this radius of convergence. Absolute value x minus a less than R, then series converge, diverge otherwise. If the ratio test was done and then you get it equal to 0, then series converges for all x value. Okay, so for all real number. Now, if it give you, if the limit does not exist, in other words, goes to infinity, then the series converge only at the one value which is equal to a. So these cases might look familiar when you guys did the ratio test. So we'll use the same one. So problem 1 and 2, find the interval of a convergence of the Taylor series representation. So you're already given that it converges certain way. So we are looking for this part here, R value. So in order to do that, we need to take the limit as n, a sub n plus 1 over a sub n equal to some number greater than 0. So let's check. Number 1, we have a function 7 divided by 1 minus x, and then luckily enough, they already wrote the Taylor series for you. Wrote it in this format here. Right, so this will be your a sub 0, a sub 1, a sub 2, all the way up to a sub n. So your a sub n, you can see that it's 7. And then you can see each a sub 1, 2, 3, all the way up to this, you're going to have a 7 repeatedly. So the next term, whatever this term, afterward will be also 7. So therefore, a sub n plus 1 over a sub n equals 7 over 7, which is equal to 1. So by the ratio test, we need to take the limit. So limit as n goes to infinity, a sub n plus 1 divided by a sub n. Well, that's limit as n goes to infinity of really 1. That's just 1, which is greater than 0. So this is your L. So R will be 1 over L, which is 1 over 1, which is 1. So we have exactly case 1. And the series converge only between x minus a, absolute value that function less than r. So converges x minus 0 less than 1. Well, by algebra, you know that this is equal to just x less than 1. To get rid of the absolute value, we set each other -1 and +1. So our Taylor series converges between -1 to 1. Okay. So let's do one more practice. Same thing. I'm going to find a sub n plus 1, and then take the limit as n approaches of infinity of our ratio. So you can see that this is your a sub 0. This part over here, this one over here, this one over here, and you can see that the format is this, right? 4 raised to the nth power. So this is your nth function. So a sub n looks like, this is your nth term, a sub n looks like -1, and then x plus 1, and 4 raised to the some nth power. I think there's a typo. This should be n. Right? So you have -1 nth power, n plus 1, 4 raised to the nth power. This part is your variable part. This part over here is your coefficient part. So if I add one more term, then you're going to have -1 raised to the n plus 1. And then n plus 2, right? 1 plus 1 is 2. And then 4, raise it to the n plus 1. Add 1 more to each term. So therefore, a sub n plus 1 over a sub n is negative 1, raise it to the n plus 1. N plus 2, 4, raise it to the n plus 1, all over negative 1, and raise it to the n plus 1. 4, raise it to the nth power. Now, you know that by algebra, this is equal to 4nth times 4 to the first power. So 4 to the n, 4 to the n disappear. Same thing. The nth disappear, giving us negative 1. Right? So leaving us negative 1 times 4, which is negative 4, n plus 2. And then on the bottom, you just have n plus 1. Distribute, final answer will be negative 4n minus 8 over n plus 1. Now, in order to find radius of convergence, we apply the ratio test, a sub n plus 1, a sub n, and we just figured that a sub n plus 1 over a sub n is negative 4n minus 8 over n plus 1. So limit as n goes to 8, negative 4n minus 8 divided by n plus 1. Okay. Now, one of the rules that we learned in chapter 2 in Math 121 when we did the limit chapter, you can divide it by the highest power, which is n. So if I do that, infinity. Keep put 8, but it should be infinity. Negative, if I divide each term by n, you have n over n, 1 over n, and plug it in 0. You know that the n's disappear and disappear, so really you get this limit as n approaches to infinity. The only surviving term, because if you plug it in really large number here, the denominator, big number, it's gonna be 0, it's gonna be 0. So you only are left with negative 4 over 1. Negative 4 over 1. Also, if you recall, if you have a same degree, you know the leading coefficient is going to be your limit value. So that's another thing that we talked about in Math 121. So you either get negative 1 over 4, but in absolute value that will be 4. So limit as n approaches to infinity, absolute value 4, which is 4 that's greater than 0. That's good. That's a case 1 again. Case 1, you get this 4 is greater than 0. So radius of convergence is 1 over 4. So we will find the x value by setting less than 4 this time. So r is equal to 1 over 4. So we have case 1 also applies, converges when x minus 0 is less than 1/4, which is just absolute value of is less than 1 over 4. To get rid of absolute value, we set both negative and positive. So this will be your area of convergence. So the polynomial only converges when x value is between negative 1/4 to positive 1/4. Okay? All right, last one. We have one more example to go. And this kind of reviews everything from 10.1 all the way up to 10.2. First part, they are asking you to come up with a Taylor polynomial. So 1 and 2, they give you the polynomial already. We didn't have to write out the Taylor polynomial. But in number 3, they give you just normal function. We have to come up with a Taylor polynomial, find the Taylor series at 0, and then determine value for our Taylor polynomial convergence. Okay, so part A is 10.1, finding the Taylor polynomial. So let's do that. How many times do we have to do? Just general form, nth degree. So let's start working on it and then see the pattern. Okay, so part A, you have f of x is equal to e to the 3x. First derivative, e to the 3x, derivative of 3x is 3. So you have 3 times e to the 3x. Second derivative, you take again 3 times e to the 3x, and then 3 derivative of 3x is 3. So you have, now I'm going to do this so that you can see the pattern. I'm not going to put 9. You can, 3 times 3 is 9, but you're going to miss the pattern. So in other words, it's 3 times e to the 3x. Let's do third time, then same thing. This whole part remains the same, right? But 3x, the derivative of 3x is 3. So it looks like we are just going to gain another 3. So I'm going to have, this is 3 times e to the 3x, but 3 gets being multiplied. So we have total 3, 3, 3, multiplying e to the 3x. So do you guys see the pattern? So fourth term, fourth derivative will be, again, 3 times 3 e to the 3x, but you get multiplied by dx another 3, so you're gaining 3 each time. So anyone see the pattern? Right, so if I did it nth times, oops. Before we do that, I don't know why I put 2, but it should be x each time. I'm going to end up having this number of derivative matches up number of 3s, right? So fourth derivative, we multiply 3 4 times, raise it to the e to the 3x. So I'm going to end up having 3 raise it to the n, e times 3x. So that will be the pattern for our derivative. Now, Taylor polynomial at 0, we are going to plug it in 0 to find the coefficient. So that's a step 1. Step 2, we plug it in the a value. So f of 0, that's e to the 3 times 0, which is e to the 0, which is 1. F first prime of 0, that's 3 times e raised to the 3 times 0, which is 3 times e to the 0, which is 3. So you can kind of see that each one, you're going to have 0, 0, 0, 0 as a exponent. So e raised to the 0, that's just going to be 1. So you're basically having 3, like 1, 3, 3 times 3, which is 9 for the next one, 27, and then 81, and so on. So I'm not going to write it out, but the second derivative, if you plug it in 0, I'm going to have just 9. The third derivative, I'm going to have 27. Fourth derivative, I'm going to have 81. So nth degree at 0 will be 3 to the n. Now, let's find all the coefficients. So step 3, I'm going to have a sub 0, which is f of 0, and then you have this factorial term. That's just f of 0, which is 1. A sub 1 term will be f prime of 0 divided by 1 factorial. So f prime of 0, which is 3. A sub 2, which is f double prime of 0 divided by 2 factorial. So that's going to be 9 over 2. F cube will be triple prime of 0 divided by 3 factorial. the triple prime at 0 is 27. Divided by 3 times 2 times 1, which is 6. So 27 over 6. A sub 4, the coefficient for the fourth term will be fourth derivative at 0, 4 factorial, which is 81 over 24, which is equal to 27 over 8. All the way up to a sub n, f of n sub 0, n factorial. So you have f of n sub 0, n factorial. So 3 to the n over n factorial. So using that coefficient, let's write out the nth degree polynomial. So that's part A, right? Almost done. So let me finish it in single page. So I'm gonna make this, I'm gonna resize it, make it small so I can fit in. So my Taylor polynomial at the nth degree will be, these are my coefficient here, 1, 3, 9 over 2, 27 over 6, 27 over 8, 3n raised it, 3 raised to the n, my divided by n factorial. So my p sub n sub x will be 1 plus 3x. The next term will be 9 over 2 because it's a second term, x to the second power. The third term, a sub 3, is 27 over 6. That's the coefficient x cubed. 27 over 8, x to the fourth, all the way up to 3 sub n, n factorial, x over n, and then goes more and more. Okay. Now, Taylor series will be just simple. So that's part B, right? So this is part A answer. We come up with a Taylor polynomial. Taylor series is easy. You just have to add what? Limit in front of our Taylor series. We got the p sub 3 raised to the k value. You just have to put the limit in front. So part B, Taylor series at a equals 0 for f of x, e raised to the 3x is very simple. Limit as n goes to infinity of p sub n sub x. Okay. So if you take the limit, then you know that the first term, there's no nth term, so it's gonna remain the same. So basically, same thing. You just have to take the limit. Okay, so very simple. Once you come up with a Taylor polynomial, Taylor series is just taking the limit of our function. Okay. All right. Last one, determine the value of x for which now we are going to actually take the limit from part B, and then see which value for the limit exists. Okay, so that's just what we did in part 1 and 2. We find a sub n plus 1, and then take the ratio and then see which value converges. So part C. Let's find out a sub n and then a sub n plus 1. A sub n, we found that a sub n is 3 raised to the n divided by n factorial. So if I add 1, that's just 3 raised to the n plus 1 factorial. So a sub n plus 1, a sub n, that's this part, this quotient, divided by this quotient here. And then all over, right? Okay, now I'm gonna rewrite it. So you have 3 raised to the n plus 1 over n plus 1 factorial. And then flip this one because I can technically multiply n, 3n, n factorial 3 raised to the n to get rid of it. Then I have n factorial here and then 3 to the n. You know that this is 3n times 3 1s, so 3 to the n disappear, only 3 surviving. This really is n plus 1 times n factorial. So n factorial disappear, so leaving me just the 3. And then you have n plus 1. Okay. All right. And then let's take the limit as n approaches to infinity. A sub n plus 1 divided by a sub n, which we got it as 3 over n plus 1. This is a bottom heavy, so by the limit rule, this goes to 0. If you plug it in really big number, then the fraction in general will be 0. So which case is it when it's equal to 0? This will be case 2. When the limit as n approaches to 0 of the ratio equals 0, then it converges everywhere. So by case 2, the final answer is, since the limit of the ratio is 0, we have case 2 applies, and then it converges for all x value. In other words, negative infinity to positive infinity. Okay, that's it for section 10.1 and 2, and then we will continue with rest of chapter 10 on the next video.